In an era dominated by the pursuit of space exploration, Elon Musk has long been a visionary, pushing humanity closer to a multiplanetary future. From the ambitious colonization plans for Mars to the Starship project, Musk has made headlines with his forward-thinking goals. However, a recent discovery made by James Webb has sent shockwaves across the globe, triggering a wave of excitement and fear alike. The discovery of city lights on Proxima b, hinting at some signs of advanced extraterrestrial life in space. That shocking revelation, according to SpaceX's CEO Elon Musk, not only transforms our understanding of the universe, but also presents a new frontier for space exploration. Join us as we dig deep into the new stunning discovery that could blow our minds. The James Webb Space Telescope was designed to peer into the farthest reaches of the universe, capturing images and data that have fundamentally changed our understanding of space. But no one anticipated that it would find something so close to home that could spark global fascination. Proxima b, located just 4.24 light-years from Earth, has always intrigued astronomers due to its position in the habitable zone, where conditions might allow liquid water to exist. Over the years, various studies have speculated about the potential for life on the planet, but no concrete evidence has emerged, until now. In a series of stunning images, James Webb revealed the unmistakable glow of artificial lighting on the dark side of Proxima b. The light pattern was unlike anything caused by natural phenomena, such as volcanic activity or bioluminescence. Instead, it bore a striking resemblance to the artificial light emitted by cities on Earth when viewed from space. The discovery was nothing short of extraordinary. For the first time in human history, we had detected a possible sign of advanced extraterrestrial technology. City lights suggest the presence of a civilization capable of generating electricity, a hallmark of technological development. While this may not confirm intelligent life definitively, it is the closest evidence we've ever had to support the idea that we are not alone in the universe. Thus, it is understandable when news of the discovery sent shockwaves around the world. For centuries, the question of whether we are alone in the universe has captivated the imagination of scientists, philosophers, and the general public alike. Now, for the first time, we had a tantalizing glimpse of the answer. The potential discovery of city lights on Proxima b ignited both awe and fear as humanity grappled with the profound implications of the find. On the one hand, the confirmation of intelligent life beyond Earth would be one of the greatest scientific breakthroughs of all time. It would validate decades of research and open up new avenues of exploration, offering insights into the nature of alien civilizations and the possibility of interstellar communication. Scientists around the world celebrated the discovery, calling it a paradigm-shifting moment in the history of space exploration. On the other hand, the discovery also raised troubling questions. What kind of civilization lives on Proxima b? Are they peaceful, or could they pose a threat to humanity? Are they aware of us, and if so, what might their intentions be? Put simply, the fear of the unknown looms large, as history has shown that encounters between civilizations of differing technological capabilities often end in conflict. Stephen Hawking, the renowned theoretical physicist, once warned against actively seeking contact with extraterrestrial civilizations, arguing that an advanced alien race might not view humanity kindly. He likened it to the encounter between Native Americans and European settlers, an encounter that did not end well for the less advanced civilization. The possibility that the inhabitants of Proxima b could be hostile has led to renewed discussions about the risks of interstellar exploration. If the city lights detected by James Webb belong to a civilization that is far more advanced than humanity, we could be opening ourselves up to unimaginable dangers. Either ways, the discovery of city lights suggests that the inhabitants of Proxima b have mastered electricity, urban planning, and possibly even advanced technologies far beyond our comprehension. For all we know, they could already be aware of us. Have they been observing Earth just as we've been searching for signs of life on other planets? Elon Musk acknowledged these concerns, but his response was characteristically optimistic. According to Musk, this discovery presents risks, yes. But progress always involves risk. The universe is far bigger and more complex than we can imagine, and we have to embrace this new reality. If we sit back in fear, we'll never grow as a species. We have to explore, to push the limits, to meet the unknown head-on. And of course, Musk is not alone in the path to Proxima b. Various agencies and organizations, both governmental and private, are eager to pave the path toward this interstellar endeavor. NASA, with its long history of space exploration, is naturally one of the most enthusiastic agencies when it comes to venturing beyond the solar system. While much of NASA's current focus is on sending astronauts back to the Moon and eventually to Mars, the agency is also investigating advanced technologies that could one day make interstellar travel a reality. Research into propulsion systems such as nuclear fusion and ion thrusters, along with long-term life support systems, could serve as foundational technology for a future human mission to Proxima b. NASA's scientific focus on discovering potentially habitable worlds makes Proxima b a natural target. The European Space Agency, also known as ESA, is another key organization with ambitions to explore beyond the solar system. ESA has contributed to missions such as Rosetta, which explored comets, and the ExoMars program, focused on Martian exploration. Like NASA, ESA is engaged in research on deep space propulsion systems and the technologies necessary for long-duration human spaceflight. A mission to Proxima b, whether robotic or human-crewed, would likely require international collaboration, making ESA a crucial partner in this ambitious goal. Elsewhere, China's space agency, CNSA, has also rapidly advanced in recent years, successfully landing rovers on the Moon and Mars and developing a space station. China's growing ambitions in space exploration suggest it could become a leading contender in future interstellar missions. With ongoing research into nuclear propulsion and plans to push further into deep space, CNSA could play a major role in any international effort to send humans to Proxima b. However, reaching Proxima b, despite its allure, still presents significant challenges that dwarf anything humanity has ever attempted. To get humans to Proxima b within a reasonable time frame, new breakthroughs in space travel technologies are essential. The immense distance between Earth and Proxima b, around 25 trillion miles, poses the first and most significant challenge. Using current space travel technology, such as chemical rockets, it would take tens of thousands of years to reach the exoplanet. Even the fastest spacecraft humanity has ever created, such as NASA's Parker Solar Probe, which can travel at a record speed of 430,000 miles per hour, equals 700,000 kilometers per hour, would take over 17,000 years to reach Proxima b. Clearly, new propulsion systems are required. Furthermore, sending humans on such a mission introduces additional complexities. Astronauts would need life support systems capable of sustaining them for decades, shielding from cosmic radiation, food and water supplies, psychological and medical care, and the ability to communicate with Earth across interstellar distances. These challenges necessitate groundbreaking technological developments. The cornerstone of any mission to Proxima b will be propulsion. To cover the 4.24 light-years separating us from our closest stellar neighbor in a human lifetime, spacecraft must travel at an extraordinary fraction of the speed of light. Fortunately, several innovative concepts are being developed to make this possible. One of the most promising ideas for interstellar propulsion is the concept of light sail technology, particularly in the form of the breakthrough Starshot project. Announced in 2016, this project envisions sending small, lightweight spacecraft called Starships to Proxima Centauri, propelled by powerful ground-based lasers. These Starships, weighing just a few grams, would be equipped with reflective sails made of ultra-thin materials. system of high-powered lasers based on Earth would focus intense beams of light onto the sails, pushing the star chips to speeds of up to 20% of the speed of light. At these velocities, a mission to Proxima b would take just over 20 years, a significant reduction from the tens of thousands of years required by conventional technology. While Breakthrough Starshot is primarily aimed at robotic probes, it demonstrates the potential of light sail propulsion. Scaling up this technology to carry human passengers is a future possibility. However, human missions would require far more powerful laser arrays and much larger sails. Additionally, technologies to decelerate spacecraft at Proxima b will need to be developed, as slowing down at interstellar speeds is no small feat. Another exciting avenue is nuclear fusion propulsion. Nuclear fusion, the process that powers the sun, involves fusing light atomic nuclei, such as hydrogen, to release vast amounts of energy. Unlike traditional chemical propulsion, which is limited by the energy density of chemical bonds, nuclear fusion promises much higher energy efficiency and the potential for sustained thrust over long durations. The direct fusion drive is one example of fusion propulsion in development. This system would use a fusion reactor to generate both heat and electricity, which could then be used to propel a spacecraft at high speeds. Theoretically, fusion-powered spacecraft could achieve speeds up to 10% of the speed of light, allowing for travel times to Proxima b on the order of 40 years. While fusion propulsion remains experimental, breakthroughs in nuclear fusion technology, such as those pursued by ITER, the world's largest nuclear fusion project, could make this concept a reality. Sustained fusion reactions in a controlled environment are difficult to achieve, but if successful, fusion propulsion could revolutionize space travel, making interstellar missions feasible within a human lifespan. For even faster travel, antimatter propulsion offers one of the most theoretically powerful means of propulsion. Antimatter is the mirror image of matter, composed of particles with opposite charges. When matter and antimatter collide, they annihilate each other, releasing energy with 100% efficiency, compared to just 0.1% efficiency for chemical reactions. Antimatter rockets would work by combining antimatter and matter in a controlled reaction to produce thrust. The amount of energy released in such a reaction is enormous, allowing for spacecraft to potentially reach up to 90% of the speed of light. In this scenario, humans could reach Proxima b in just over 4 years. The major challenge with antimatter propulsion is production and storage. Currently, producing antimatter is an incredibly inefficient and expensive process, requiring vast amounts of energy to create even tiny quantities. Storing antimatter is also problematic, as it must be kept separate from matter, lest it annihilate and release its energy prematurely. However, if these challenges can be overcome, antimatter propulsion could be the key to rapid interstellar travel. Even with advanced propulsion systems, the journey to Proxima b would take decades, possibly longer. This raises a host of challenges related to life support, habitation, and the psychological well-being of astronauts. Traditional life support systems used on the International Space Station, or ISS, rely on resupply missions from Earth. This model is unsustainable for long-duration interstellar missions where resupply is impossible. Instead, interstellar missions would require closed-loop life support systems, which recycle air, water, and food to sustain life indefinitely. NASA is already working on such systems for future missions to Mars. For example, the Environmental Control and Life Support System on the ISS recycles wastewater into drinking water and converts carbon dioxide back into oxygen. However, these systems will need to be greatly improved to support multi-decade missions. Food production in space, using technologies like hydroponics or bioreactors, will also be essential. On the other hand, cosmic radiation is a major concern for long-duration space travel. In deep space, away from the protection of Earth's magnetic field, astronauts are exposed to harmful radiation from the sun, and from distant supernovae and black holes. Over decades, this radiation could cause serious health problems, including cancer and neurological damage. One potential solution is active shielding, where electromagnetic fields are used to deflect incoming radiation. This concept mimics Earth's magnetic field, which protects life from solar and cosmic radiation. Another idea is passive shielding, where materials such as water or hydrogen-rich compounds are used to absorb radiation. In addition, prolonged exposure to microgravity, such as that experienced by astronauts aboard the ISS, can lead to muscle atrophy, bone loss, and other health problems. To mitigate these effects, spacecraft bound for Proxima b may need to generate artificial gravity. One proposed method is centrifugal force, where sections of the spacecraft rotate to create gravity through acceleration. This would help maintain the physical health of astronauts during the long journey. Given the long journey times, some researchers have proposed alternative methods for transporting humans to Proxima b, such as hibernation. Hibernation, or suspended animation, is a state of reduced metabolic activity that could allow astronauts to survive long space journeys with minimal resource consumption. By slowing down bodily functions, hibernating astronauts would require less food, oxygen, and water. This would reduce the overall weight of the spacecraft, making it easier to accelerate to high speeds. Researchers have already begun studying the possibility of inducing hibernation in humans. Techniques used on animals, such as lowering body temperature or using certain drugs, could potentially be adapted for human space travel. Hibernation would also help mitigate the psychological strain of long-duration missions, as astronauts would spend much of the journey unconscious. If hibernation proves unfeasible, another option is to use generational ships, where multiple generations of humans live and die aboard the spacecraft during the journey to Proxima b. This concept involves creating large, self-sustaining spacecraft that function as floating ecosystems capable of supporting human life for centuries. Generational ships would need to be equipped with advanced life support systems, food production facilities, and medical care. However, the social and psychological challenges of living on a spacecraft for multiple generations, cut off from Earth, would be immense. After all, the path to taking humans to Proxima b is undoubtedly filled with challenges, but the rewards could be extraordinary. Discovering new worlds, potentially even new life forms, represents the next great leap for humanity. With breakthroughs in propulsion technologies, life support systems, and alternative travel methods like hibernation or generational ships, interstellar travel is becoming more than just a dream. While many of these technologies are still in their infancy, progress is being made at an accelerating pace. The journey to Proxima b may take decades or even centuries, but with each new breakthrough, we inch closer to realizing the audacious dream of traveling beyond our solar system. In the not-too-distant future, humans may stand on the surface of an alien world, gazing up at Proxima Centauri and reflecting on the breathtaking journey that brought them there. In the meantime, let's explore some of the most exciting recent discoveries of exoplanets and the implications they hold for the search for extraterrestrial life. Among the most intriguing discoveries in recent years is the detection of super-Earths, a class of exoplanets that are larger than Earth but smaller than Neptune. These planets often have rocky surfaces and atmospheres, making them some of the most promising candidates for habitability. One such planet is TOI 1452b, a super-Earth discovered by TESS in 2022. Located about 100 light-years from Earth, TOI 1452b is thought to have a surface covered in oceans, possibly making it a water world. The prospect of a planet entirely covered by a global ocean is tantalizing, as it raises the possibility of aquatic life forms evolving in an environment similar to Earth's early oceans. In addition to TOI 1452b, several other super-Earths have been discovered in recent years. LHS 1140b, located about 40 light-years away, is another super-Earth with a rocky surface and an atmosphere that could potentially support life. With a mass about 6 times that of Earth, LHS 1140b orbits within its star's habitable zone, where temperatures could allow liquid water to exist. Observations from telescopes like James Webb are expected to provide more detailed information about the composition of its atmosphere, which could reveal signs of habitability. Another exciting category of exoplanets that has emerged in recent discoveries is the mini-Neptune class. These are planets that are larger than Earth but smaller than Neptune, with thick atmospheres composed primarily of hydrogen and helium. Mini-Neptunes are of particular interest because they represent a middle ground between rocky planets like Earth and gas giants like Jupiter, providing valuable insights into planet formation. One notable example is K2-18b, a mini-Neptune discovered by the Kepler mission. Recent observations from the Hubble Space Telescope have revealed that K2-18b's atmosphere contains water vapor, making it the first exoplanet with water in its atmosphere located within its star's habitable zone. While K2-18b is too large to be considered Earth-like, the presence of water vapor in its atmosphere raises important questions about the potential for habitability on mini-Neptunes. Scientists speculate that beneath the thick hydrogen-helium atmospheres of these planets, there could be rocky cores with liquid water oceans. If future observations confirm the presence of water oceans beneath the atmospheres of mini-Neptunes, these planets could represent a new type of potentially habitable world, one vastly different from Earth but still capable of supporting life. The search for exoplanets often focuses on finding planets within the habitable zone of their parent stars, the region where conditions are just right for liquid water to exist on a planet's surface. One of the most exciting recent discoveries in this regard is Proxima Centauri b, the closest exoplanet to Earth, located just 4.2 light-years away. Discovered in 2016, Proxima Centauri b orbits its star within the habitable zone, and recent studies suggest that it could have a rocky surface with liquid water. Although Proxima Centauri is a red dwarf star and its planet is exposed to intense stellar flares, making habitability a challenge, its proximity makes it a prime target for future observations and potentially even exploration missions. Another exciting discovery is the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a red dwarf star located about 39 light-years from Earth. 3 of these planets lie within the habitable zone, where conditions could allow for the presence of liquid water. The TRAPPIST-1 system has captivated astronomers since its discovery in 2017 because all 7 planets are roughly the size of Earth and could have atmospheres suitable for life. The James Webb Space Telescope is expected to conduct detailed studies of the TRAPPIST-1 planets, providing insights into their atmospheric compositions and potentially identifying biosignatures. Another intriguing category of exoplanets that has emerged from recent discoveries is ultra-short-period planets, or planets that orbit their stars in just a matter of hours or days. One example is NGTS-10b, a Jupiter-sized gas giant that orbits its star in just 18 hours. Located about 1,000 light-years from Earth, NGTS-10b's close orbit causes its atmosphere to be extremely hot, with surface temperatures reaching thousands of degrees Fahrenheit. While such planets are unlikely to host life, they provide valuable insights into the extreme conditions that can exist on exoplanets and help refine models of planetary formation and evolution. Another ultra-short-period planet of interest is TOI 849b, a naked planet core, discovered by TESS in 2020. TOI 849b orbits its star in less than a day and is believed to be the exposed core of a gas giant, stripped of its atmosphere by intense stellar radiation. This discovery offers a unique opportunity to study the interior structure of a planet, as TOI 849b provides a rare glimpse into the composition of a planet's core. Understanding the makeup of this planet could help scientists learn more about the processes that shape the formation of gas giants and their eventual evolution. While many exoplanet discoveries have been made within a few hundred light-years of Earth, recent advancements in telescope technology have allowed astronomers to detect planets orbiting stars much farther away. One such discovery is OGL 2016 BLG 1195LB, a planet located more than 13,000 light-years away. This planet was discovered using a technique called gravitational microlensing, which relies on the gravitational field of a distant star to magnify the light from a background star, revealing the presence of an orbiting planet. OGL 2016 BLG 1195LB is similar in size to Earth and orbits a star in the outer regions of the Milky Way, providing valuable data about the distribution of planets across the galaxy. Another distant discovery is Kepler 1649c, a rocky exoplanet located about 300 light-years away that orbits its star within the habitable zone. Kepler 1649c is similar in size to Earth and receives about 75% of the sunlight that Earth does from the Sun, making it one of the most Earth-like planets discovered to date. Although its distant location makes it difficult to study in detail, Kepler 1649c remains a prime candidate for future research, as its Earth-like characteristics make it a potential target in the search for extraterrestrial life. Fascinatingly, the launch of the James Webb Space Telescope in December 2021 marked a new era in exoplanet research. One of the most groundbreaking contributions of James Webb to exoplanet research is its ability to analyze the atmospheres of these distant worlds. By observing transiting exoplanets, those that pass in front of their host stars from our viewpoint, James Webb can measure the light that filters through an exoplanet's atmosphere. This technique, known as transmission spectroscopy, allows scientists to determine the chemical composition of the atmosphere, identify potential biosignatures, and assess habitability. For example, James Webb's early observations included the atmosphere of WASP-39b, a gas giant located about 700 light-years away. The telescope detected water vapor in the atmosphere, confirming the presence of this essential molecule for life. This discovery not only demonstrated James Webb's capabilities, but also set a precedent for future studies aimed at characterizing the atmospheres of other exoplanets. By identifying other molecules such as carbon dioxide, sodium, and possibly even methane, James Webb is providing crucial insights into the conditions present on these distant worlds. Additionally, Webb's sensitivity and advanced spectroscopy techniques allow it to search for potential biosignatures in exoplanet atmospheres. Scientists are particularly interested in detecting molecules such as oxygen, ozone, methane, and carbon dioxide, which can suggest the presence of life. One exciting aspect of Webb's mission is its ability to simultaneously detect multiple biosignatures. For instance, a simultaneous detection of both methane and oxygen in an exoplanet's atmosphere could indicate the presence of biological activity, as these gases tend to react chemically and are often replenished by living organisms. This dual approach to biosignature detection represents a significant advancement in the search for extraterrestrial life. Moreover, Webb's capabilities extend to rocky, Earth-like exoplanets, particularly those located in the habitable zones of their host stars, the regions where conditions might support liquid water. The telescope's sensitivity and advanced imaging techniques allow it to search for potentially habitable exoplanets with greater precision. One of the most anticipated targets for James Webb is the TRAPPIST-1 system, which contains several Earth-sized planets orbiting a cool dwarf star. By studying the atmospheres of these planets, scientists hope to gather insights into their potential for supporting life. The ability to analyze the atmospheres of these worlds opens the door to assessing their habitability and searching for signs of life. marking a significant leap forward in our quest to find another Earth-like planet. Additionally, the Webb telescope is expected to focus on other intriguing targets, such as Proxima Centauri b, the closest known exoplanet to Earth, and LHS 1140b, a super-Earth located approximately 40 light-years away. These observations could provide critical data on the conditions present on these planets and their potential for habitability. In short, with its advanced capabilities, James Webb is poised to significantly expand our current catalog of exoplanets. Its sensitivity and range will enable astronomers to discover more exoplanets, including those that are smaller and more Earth-like than previously detectable. This will contribute to a more comprehensive understanding of how planetary systems form and evolve, potentially offering insights into the origins of our own solar system. Moreover, observations made by James Webb will complement and enhance data collected by other missions, such as TESS. As TESS continues to discover new exoplanets, James Webb will provide the means to analyze their atmospheres and characteristics, creating a more holistic view of exoplanet science. Put exoplanets aside, there is a new, remarkable observatory made by the aging Hubble telescope. At the center of almost every large galaxy in the universe sits a supermassive black hole, and any surrounding clouds of gas, dust, or even stars that wander too close are consumed as they cross over the event horizons of these cosmic monsters. When supermassive black holes gorge on large volumes of energy and matter in this way, they become capable of creating massive jets of plasma that are shot out through space at close to the speed of light. For instance, one such galaxy, Messier 87, which is roughly 54 million light-years from Earth, is home to a 6.5 billion solar mass supermassive black hole, which produces 3,000 light-year-long jets of plasma. And new research, based on observations made by the Hubble Space Telescope, has found that double-star systems sitting close to these jets are living pretty risky lives. Stars can often find themselves gravitationally bound to one another, forming double-star systems. And sometimes an aging, swelled-up normal star can find itself with a white dwarf companion, the dead embers of a once active star. In such scenarios, the enlarged star can shed its materials, mainly hydrogen, which are gravitationally drawn to the dense white dwarf. However, as hydrogen accumulates on the surface of the white dwarf, the star can reach a critical tipping point. After that point, the process spurs an explosion. You can think of it like a hydrogen bomb. Such explosions are called nova, and they are relatively common throughout the universe. In fact, one is expected to happen quite soon, with a star called T Coronae Borealis. And, in a rare turn of events, scientists think that explosion will be bright enough to make a new star show up in our night sky. Intriguingly, astronomers found that nova eruptions are almost twice as likely to occur in double-star systems located in the vicinity of Messier 87's supermassive black hole plasma jets. Initially, astronomers thought something about the jets might be enhancing the fueling process and therefore the rate of explosions, or even birthing new double-star systems in its vicinity. But Alec Lessing, an astronomer from Stanford University and lead author of the paper reporting on these findings, isn't quite convinced. According to Lessing, "We don't know what's going on, but it's just a very exciting finding. This means there's something missing from our understanding of how black hole jets interact with their surroundings." Not long after Hubble was launched in 1990, astronomers pointed the telescope towards the center of Messier 87, where the galaxy's supermassive black hole dwells. At the time, they observed strange blue transient events near the black hole, but the narrow field of Hubble's camera at the time meant the scientists couldn't compare how often these events were occurring in that location when compared to the rest of the galaxy. In the words of said co-author Michael Shara from the American Museum of Natural History in a press release, We're not the first people who've said that it looks like there's more activity going on around the M87 jet. But Hubble has shown this enhanced activity with far more examples and statistical significance than we ever had before. The evidence for the jet's influence on the surrounding stars was collected over a 9-month period, with Hubble observing with its newer, wider-view camera every 5 days. Despite nova eruptions being common events in galaxies as a whole, the new research further illustrates the influence that supermassive black holes can have on activity and evolution of galaxies. Some of the most impressive objects in our universe are supermassive black holes. Weighing in at millions, billions, or even tens of billions of solar masses, they're the heaviest single objects contained within the known universe. One of the great problems in modern astrophysics is the open question of how they formed and grew up, and in many ways, the dawn of the James Webb era has only intensified that problem. Looking back toward the dawn of time, we find supermassive black holes existed even very early on, reaching hundreds of millions or even a billion solar masses by the time only a few 100 million years had elapsed, when the universe was just a few % of its current age. Was it just plain old astrophysics that led to their creation, with nothing special happening to seed them? Or is it possible that the universe was actually born with seed black holes that would rapidly grow into the supermassive behemoths we observe much later on? Or does James Webb just find some hints of our previous universe? All this and more will be discussed in today's episode. Let's start with one relevant plot that we can look at as our starting point. A plot of the inferred black hole masses in these early galaxies from when the universe was around 5% of its current age, versus the total mass inferred to be in the form of stars. The reason this plot is important is that today, when we plot the more typical black hole to stellar mass ratio of galaxies, as shown in the gray-shaded regions, we get a value that's more typically around 0.1%, indicating that earlier on, galaxies may have had more massive black holes compared to the amount of stars inside. For example, take the black hole at the center of the galaxy Messier 87, one of the largest, most massive, and brightest galaxies within 100 million light-years of our own. It contains within it an enormous supermassive black hole, one that weighs in at 6.5 billion solar masses, or some 1,500 times as massive as the Milky Way's largest black hole. But it also contains an enormous number of stars, around 1 trillion of them, with an estimated stellar mass of around 2.4 trillion solar masses. The supermassive black hole to stellar mass ratio for this galaxy, which contains the largest supermassive black hole in our vicinity, still only comes in at a paltry 0.27%. If central supermassive black holes and galaxies formed together and grew up together, we'd expect that ratio to remain relatively constant over time. As galaxies grow and grow, so would their supermassive black holes, keeping pace with one another. However, the possibility that many would love to consider is that perhaps the universe didn't form early black holes and early stars concurrently, and that those two components of the galaxy grew up together. Instead, perhaps the universe was born with a set of primordial black holes, or black holes that formed in the immediate aftermath of the hot Big Bang, and then those black holes served as nucleation sites for galaxies to form around and grow. However, there are two other ways to make black holes in the universe that fall within the standard history scenario that don't involve primordial black holes, or black holes formed in the immediate aftermath of the Big Bang at all, but merely conventional astrophysics. Instead of being born with black holes, the universe could have simply been born with normal, slight density imperfections, tiny fluctuations that result in initially overdense and underdense regions. Those overdense regions could slowly grow, attracting more and more matter, until one of two things occurs. First, stars can form from this matter, resulting in massive stars that burn through their fuel quickly and die, with their cores collapsing and resulting in seed, black holes of tens, hundreds, or maybe even up to 1,000 solar masses. Second, cold streams of gas can fall into these overdense regions and collide with one another, which could form stars like normal. However, alternatively, it could lead to a phenomenon known as direct collapse, where the matter becomes dense enough in a small enough volume of space that black holes can directly form, leading to a population of much heavier black hole seeds in the range of tens of thousands or even hundreds of thousands of solar masses. The first one definitely happens, but the second one could happen as well, and requires no new physics to trigger it, unlike the primordial black hole scenario. Although it might not seem like a big deal, the difference between a primordial black hole, a stellar mass black hole, and a heavy seed formed via direct collapse is extremely significant. When we're looking at galaxies in the very early universe, we're seeing the universe as it was an incredibly long time ago, more than 90% of the universe's history ago. Even back prior to the James Webb era, we were finding galaxies with large, massive black holes that were comparable to 1 billion solar masses from when the universe was between 650 and 800 million years old, just 5 to 6% of its current age. Now, in order for a black hole to get that big that fast, it must have grown up quickly. Based on the physics that we know, there's a limit to how quickly a black hole can grow from devouring matter, the Eddington limit. If we extrapolate from the black holes we observe at those early times, but not super early times, back to the very early universe, we find that if we go back to when we expect the first stars to form and the first streams of cold gas to collide, we're looking at time periods when the universe was just 50 to 150 million years old, and we can infer the size and mass of the seeds we need. It turns out that one of the options, to invoke a standard astrophysics and stellar mass black hole seeds, also known as light seeds, is ruled out by the data. The situation only worsened in the James Webb era, as the record for earliest supermassive black hole was pushed back earlier and earlier. In July of 2023, Webb's researchers from the SEERS collaboration reported the discovery of SEERS 1019, which contains a black hole of 9 million solar masses from an age of 570 million years, representing 0.1% of the stellar mass inside the galaxy. Then, a few months later, a galaxy known as U8Z1 was found, at an age of 470 million years, with a rather large black hole mass of 10-100 million solar masses, but with a small stellar mass content also between 10-100 million solar masses, where the black hole is 10-100% of the stellar mass content of the galaxy. And galaxy GN Z11, as shown in January of 2024, contains a supermassive black hole of 1.53 million solar masses, just 440 million years after the Big Bang, although its stellar mass content is large at close to 1 billion solar masses, and it appears to be undergoing super Eddington accretion right now. In other words, what we're seeing suggests a mix of light and heavy seeds as the origin of supermassive black holes, but doesn't suggest a need for even earlier, truly primordial black holes. Seeds of 10,000 to 100,000 solar masses are completely sufficient for everything we see, even if those initial black hole seeds didn't arise until up to 150 million years after the Big Bang. However, the direct observation of what we call overmassive, or in some corners, outsized black holes, such as UHZ1, and also, as suggested more weakly by the more recent Ruby's paper, rules out the light seed scenario very thoroughly, as a team led by Fabio Pacucci predicted would occur back in 2017. If you begin with heavy, black hole seeds that are driven by cold streams of colliding gas and forming via a direct collapse mechanism, you'd expect to find overmassive black holes early on, and you'd expect that to be the norm. With black hole to stellar mass ratios of Shakur 10 to 100% in early, low-mass galaxies, of 110% later on in more massive, more evolved galaxies, of 0.1 to 1% in still more evolved galactic populations, and then declining to the more standard 0.1% as seen in present-day galaxies. In a compilation of James Webb observed galaxies from the first 1.5 billion years of cosmic history, Piccucci's team was able to show precisely this predicted evolutionary trend, using galaxies primarily extracted from Webb's Sears, Jades, and Glass observing programs. Although there are still uncertainties on these values, they strongly suggest a heavy seed formation mechanism, as the below graph illustrates. So what, then, of the primordial black hole scenario? The issue is twofold. If you want to form primordial black holes, your universe needs to be born with enormous magnitude overdensities, or regions where the density is more than 68% greater than the cosmic average density. If you have a region that's more overdense than that, you can prove that it will, in fact, collapse rapidly to form a black hole, and that's the primary scenario by which you can form primordial black holes that will persist until the present day. Unfortunately, there are two reasons that such a scenario is strongly disfavored. The first comes from direct observations of the universe, which give us a series of constraints concerning how much matter, out of the total amount of normal and dark matter combined, is allowed to be in the form of primordial black holes of varying masses. At low masses, that is below the mass of a typical large asteroid, black holes that were born at the start of the hot Big Bang would have evaporated, and the lack of that evaporative radiation rules them out. From about moon-mass objects to brown dwarf masses, direct searches for microlensing events rule out more than a few percent of the mass being in the form of black holes. But for heavier masses, from the lowest stellar masses on upward, the lack of gravitational wave signals, the lack of accretion signals, and the lack of features appearing in the CMB, also known as the cosmic microwave background, strongly constrain the abundance and presence of these heavier mass primordial black holes. If we wanted to create primordial black holes that were great enough in mass to serve as seeds for the black holes we observe in the late-time universe, they would have to be at least 100 solar masses in magnitude back when they were first created. However, that's just about the threshold that would mess up the fluctuations in the cosmic microwave background. It's a very challenging scenario to create them. But there's a second, arguably even stronger reason to disfavor the emergence of a large population of primordial black holes. Remember, to create a black hole primordially, in the aftermath of the Big Bang, you need an enormous initial overdensity, something that's 68% greater in density than average. But we already know the spectrum of overdensities in the universe from cosmic inflation. It has a large-scale amplitude of just c-0.03%, and that amplitude drops as we move to smaller and smaller cosmic scales. The only way to produce such a population is with a finely tuned phase transition. This transition could have occurred at the end of inflation at the electroweak scale during the formation of protons and neutrons, or during some yet undiscovered transition later on. However, this requires that we have a spike of giant magnitude overdensities, about 68% or more, at one particular mass, and then at all other scales, the overdensities are just of that standard 0.03% value. It's not only a highly constrained scenario from observations, it's one where you have to contort your theory tremendously to produce the primordial population of black holes you desire. So, at the end of the day, Could the supermassive black holes we see have arisen from a population of primordial black holes that sprang into existence in the extremely early stages of the hot Big Bang? The real answer is that it's a scenario that is neither supported nor favored by the data, but that isn't completely ruled out just yet either. It is plausible that higher resolution studies of the CMB can place stronger constraints on such a scenario, but the most promising line of evidence to find out for sure will be to push the cosmic limits even farther, looking for galaxies with black holes in them even earlier in the universe's history, from the first 150–400 million years. If the heavy seed scenario is the right one, this should be the place to look to confirm it. In addition, James Webb might be able to help, but deep observations in other wavelengths of light, such as X-ray wavelengths, would be ideal. X-rays are a form of electromagnetic radiation with much shorter wavelengths and higher energy than visible light. They are produced by extremely hot and energetic processes in the universe, such as the accretion of matter onto black holes, supernova explosions, and the collision of galaxies. X-ray emissions, particularly in the case of black holes, often originate from the regions just outside the event horizon, the so-called accretion disk, where gas and dust spiral inward, heating up to millions of degrees as they fall toward the black hole. Observing the universe in X-ray wavelengths allows astronomers to study phenomena that would otherwise remain invisible to optical telescopes. Black holes, for instance, emit little to no light directly, but their presence can be inferred by detecting the intense X-ray radiation from their surroundings. Thus, X-ray astronomy serves as one of the most crucial tools in the study of black holes, particularly ancient and distant black holes, which may hold the keys to understanding the early universe. Current space telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have been instrumental in advancing our knowledge of black holes. They have provided astronomers with detailed X-ray observations of both stellar mass black holes and supermassive black holes at the centers of galaxies. However, these observatories are limited in their ability to explore the most distant and ancient black holes due to their sensitivity and resolution constraints. The X-ray emissions from black holes that formed in the early universe are faint and difficult to detect, often drowned out by other cosmic sources. Moreover, while these observatories have significantly advanced our understanding of how black holes interact with their environments, such as by ejecting jets of material at near-light speeds or by influencing star formation rates in their host galaxies, there is still much we don't know. The formation of the first black holes, their role in the evolution of the early universe, and the mechanisms by which supermassive black holes grew so quickly in the first billion years after the Big Bang remain unanswered questions. But upcoming missions aim to bridge this gap and offer new insights into the early universe's most massive and mysterious objects. The Athena, also known as Advanced Telescope for High-Energy Astrophysics mission, scheduled for launch by ESA in the late 2030s, is set to be the next major leap in X-ray astronomy. Athena will have unprecedented sensitivity, allowing it to detect X-ray emissions from some of the earliest and most distant black holes in the universe. By capturing faint X-rays emitted by black holes at high redshifts, meaning from a time when the universe was less than 1 billion years old, Athena will provide insights into how the first black holes formed and evolved. Athena's Wide Field Imager and X-ray Integral Field Unit will offer high-resolution observations of black holes and their surroundings. These instruments will help astronomers study black hole feedback, the process by which black holes regulate star formation and heat up the gas in their host galaxies. By observing black hole feedback in galaxies at various stages of their evolution, Athena will shed light on the complex relationship between black holes and their host galaxies. Another future mission, NASA's proposed Lynx X-ray Observatory, is designed to complement and surpass the capabilities of current X-ray telescopes. Lynx aims to have 100 times the sensitivity of Chandra, making it one of the most ambitious space telescopes in development. If funded and built, Lynx would be able to detect individual black holes forming just hundreds of millions of years after the Big Bang. Lynx's high-resolution X-ray imaging will allow astronomers to map the environments around supermassive black holes in distant galaxies, offering clues to how these objects grew so rapidly in the early universe. One of the major questions Lynx aims to answer is whether these ancient supermassive black holes formed from the direct collapse of massive gas clouds, or whether they grew from smaller seed black holes over time. Moreover, Lynx will allow astronomers to study the population of intermediate mass black holes, those between stellar mass and supermassive black holes, whose existence has long been theorized but remains elusive. These intermediate mass black holes could represent a key stage in the growth of supermassive black holes, and their detection would help bridge the gap in our understanding of black hole formation and growth. The future of X-ray observations will also be closely linked to the rise of multi-messenger astronomy, the coordinated observation of cosmic events using multiple types of signals, including gravitational waves and electromagnetic radiation. Black holes are prime targets for multi-messenger observations because their mergers, for instance, produce both gravitational waves and X-ray emissions. Gravitational wave observatories like LIGO and Virgo have already detected several black hole mergers, but the combination of these signals with X-ray observations will offer a more complete picture of black hole evolution. When a black hole merger occurs, X-ray telescopes like Athena or Lynx could observe the aftermath, revealing how the newly merged black hole interacts with its surroundings. This will provide astronomers with a unique opportunity to study black holes in real time. In short, as we look to the future, it is clear that the next generation of X-ray observatories will play a crucial role in uncovering the secrets of black holes, especially those that formed in the early universe. With missions like Athena and Lynx on the horizon, we are poised to explore the most distant and ancient black holes ever detected. These observations will not only help us understand the formation and growth of black holes, but will also shed light on the broader processes that shaped the evolution of galaxies and the universe itself. By pushing the boundaries of X-ray astronomy, scientists hope to answer fundamental questions about the origins of supermassive black holes, the nature of dark matter, and the dynamics of cosmic evolution. The next decades of exploration will likely reshape our understanding of black holes and provide a more complete picture of the universe's history. In the meantime, let's take a quick look at recent observations of black hole. Using the Hubble Space Telescope, astronomers have discovered the closest massive black hole to Earth ever seen, a cosmic titan frozen in time. As an example of an elusive, intermediate mass black hole, the object could serve as a missing link in understanding the connection between stellar mass and supermassive black holes. The black hole appears to have a mass of around 8,200 suns, which makes it considerably more massive than stellar mass black holes, with masses between 5 and 100 times that of the Sun, and much less massive than aptly named supermassive black holes, which have mass millions to billions that of the Sun. The closest stellar mass black hole scientists have found is called Gaia BH1, and it sits only 1,460 light-years away from us. The newly found intermediate mass black hole, on the other hand, dwells in a spectacular collection of about 10 million stars called Omega Centauri, which sits around 18,000 light-years from Earth. Interestingly, the fact that the frozen black hole appears to have stunted its growth supports the idea that Omega Centauri is the remains of an ancient galaxy cannibalized by our own galaxy. This would suggest Omega Centauri is actually the core of a small, separate galaxy whose evolution was cut short when the Milky Way swallowed it. If this event had never happened, this intermediate black hole may have possibly grown to supermassive status, like the Milky Way's own supermassive black hole, Sagittarius A, which has a mass 4.3 million times that of the Sun and is located 27,000 light-years from Earth. That discovery is so important because these intermediate mass black holes with masses between a few hundred and a few thousand times that of the Sun have, for the most part, seem to have avoided detection. That's because, like all black holes, these mid-sized cosmic titans are marked by outer boundaries called event horizons. The event horizon is the point at which the gravitational influence of a black hole becomes so immense that not even light is fast enough to escape it. Thus, black holes are only visible in light if they are either surrounded by matter to feed on, which glows while heating up, or rip apart and feed on an unfortunate star in a so-called tidal disruption event. Intermediate black holes, like the one in Omega Centauri, aren't surrounded by a lot of matter and feeding. That means astronomers have to be a little bit cunning when hunting for such black holes. They use the gravitational effects these voids have on matter, like stars that orbit them, or on light passing through them. This new discovery's team used the former method. The hunt for this intermediate black hole began in 2019 when Nadine Neumeier of the Max Planck Institute for Astronomy, or MPIA, and Anil Seth of the University of Utah designed a research project to improve our understanding of Omega Centauri's formation history. In particular, the researchers and collaborator Maximilian Heberle, an MPIA PhD student, wanted to find rapidly moving stars in Omega Centauri that would prove the star cluster has a massive, dense, or compact central engine black hole. A similar method was used to determine the mass and size of SGR-8A using a fast-moving population of stars at the heart of the Milky Way. Haberle and team used over 500 Hubble images of this star cluster to build a vast database of the motions of stars in Omega Centauri, measuring the speeds of about 1.4 million stars. This ever-repeating view of Omega Centauri, which Hubble conducted not out of scientific interest, but rather to calibrate its instruments, was the ideal dataset for the team's mission. Looking for high-speed stars and documenting their motion was the proverbial search for a needle in a haystack. The team ultimately found not one, but 7 needle-in-haystack stars, all moving at rapid velocities in a small region at the heart of Omega Centauri. The rapid speed of these stars is caused by a concentrated mass nearby. If the team had only found one rapid star, it would have been impossible to determine whether its speed was the result of a large and close central mass, or if that star is a runaway moving at a rapid pace in a straight path, absent of any central mass. Spotting and measuring the different velocities and directions of 7 stars allowed this determination to be made. The measurements revealed a centralized mass equivalent to 8,200 suns, while visual inspections of the region revealed no objects that resemble stars. That is exactly what would be expected if a black hole was located in this region, which the team determined to be light months wide. The fact that our galaxy has matured enough to have grown a supermassive black hole at its heart means it has probably outgrown the stage of possessing many intermediate mass black holes of its own. This one exists in the Milky Way because the cannibalization of its original galaxy happened to curtail its growth processes. Of course, that doesn't really change the status of SGR-A as the closest supermassive black hole to Earth, or Gaia BH1's status of the closest stellar mass black hole to Earth. But it provides some reassurance that scientists are on the right track when considering how our central black hole became such a cosmic titan in the first place. Elsewhere on Earth, an experiment using beams of protons to probe how plasma and magnetic fields interact may have just solved the mystery of how quasars and other active supermassive black holes unleash their relativistic jets. Let's picture the scene at the heart of a quasar. a supermassive black hole, perhaps hundreds of millions, or even billions, of times the mass of our sun, is ravenously devouring matter that is streaming into its maw from a spiraling, ultra-hot disk. That charged matter is called plasma, and it gets gravitationally drawn into the black hole's surroundings. However, not all of the plasma, which is made from ionized or electrified atoms shorn of electrons, is swallowed by the black hole. Indeed, the black hole bites off more than it can chew, and some of the plasma is spat out in jets collimated by the black hole's powerful magnetic field before that plasma gets anywhere near the event horizon, which is basically the point of no return. These jets can stretch thousands of light years into space. However, explaining the physics that takes place at the base of the jet, where they're formed, has eluded scientists. The answer may have come from researchers at the Princeton Plasma Physics Laboratory, or PPPL, in New Jersey, who were able to devise a modification to a plasma measuring technique called proton radiography. In their experiment, the researchers first created a high-energy density plasma by firing a pulsed 20-joule laser beam at a plastic target. Then, they used powerful lasers to instigate nuclear fusion in a fuel capsule filled with deuterium and helium-3. The fusion reactions released bursts of protons and X-rays. These protons and X-rays then passed through a nickel mesh filled with tiny holes. Think of the mesh as like a colander for straining pasta. It strains the protons into many discrete beams that then can measure how the expanding plasma plume interacts with a background magnetic field. Because the protons are charged, they'll follow the magnetic field lines as they are buffeted by the plasma. The X-ray burst acts as a check. Because the X-rays pass cleanly through the mesh and the magnetic field, they provide an undistorted image of the plasma to compare to the proton beam measurements. As Will Fox, the experiment's principal investigator, said in a statement, "Our experiment was unique because we could directly see the magnetic field changing over time. We could directly observe how the field gets pushed out and responds to the plasma in a type of tug-of-war." They observed in detail the magnetic field bending outward under pressure from the expanding plasma, with the plasma sloshing against the magnetic field lines. This bubbling and frothing of the plasma is known as magneto-Rayleigh-Taylor instability, and it created shapes in the magnetic field that look like whorls and mushrooms. Crucially, as the plasma energy decreased, the magnetic field lines were able to snap back. This compressed the plasma into a straight, narrow column, not unlike a quasar's relativistic jet. According to PPPL's Sophia Malko, when we did the experiment and analyzed the data, we discovered we had something big. Observing magneto-Rayleigh-Taylor instabilities arising from the interaction of plasma and magnetic fields had long been thought to occur, but had never been directly observed until now. This observation helps confirm that this instability occurs when expanding plasma meets magnetic fields. The experiment strongly indicates that quasar jets can thank this sort of reaction of magnetic fields to the expanding plasma for their creation. If the results are a snapshot of what happens around active black holes, that would mean, in the black hole's accretion disk, conditions become so intense that the plasma in the disk is able to push against the tightly packed magnetic field lines, which can then snap back and push the plasma into a narrow column, almost squirting it away from the black hole. If true, this might be a huge missing piece in our picture of how active black holes operate. In the pursuit of understanding the origins of the universe, James Webb continues to rewrite the cosmic story. From unveiling the mysteries of distant exoplanets to glimpsing the formation of stars and galaxies, the Webb telescope has proven itself a groundbreaking tool. But perhaps one of the most astonishing revelations came when the telescope detected a primordial galaxy, so ancient that it seems to have existed at the very dawn of time. As astronomers delve into this remarkable discovery, it becomes clear that there's no going back to the theories we once held. Join us as we dig deep into how James Webb could rewrite our cosmology. The first stars, often referred to as population 3 stars, represent one of the most fascinating yet elusive mysteries in cosmology. These stars are thought to have formed soon after the Big Bang, emerging in the cosmic dark ages to light up the universe for the first time. Despite years of theoretical models and observations from powerful telescopes, the more we learn about these stars, the more we realize how little we truly understand. Our current understanding of the first stars is largely based on theoretical models. According to these models, the universe was a dark, opaque place for several 100 million years after the Big Bang. During this time, no stars or galaxies existed. The universe consisted primarily of hydrogen and helium, the lightest and simplest elements created in the Big Bang. As these gases cooled and began to condense under the force of gravity, the first stars ignited. These population 3 stars are believed to have been much more massive than the stars that exist today, with estimates ranging from 10 to several hundred times the mass of the Sun. The reason for this is that they formed in an environment devoid of heavier elements, which are often referred to as metals in astrophysical terms. Without metals to cool the gas clouds, these stars could accumulate far more mass before collapsing and triggering nuclear fusion. Once they ignited, they burned brightly, but lived very short lives, perhaps only a few million years, before ending in spectacular supernova or collapsing into black holes. This general picture of the first stars has been developed over decades of simulations and models. These stars were the first to fuse hydrogen into helium, and they played a crucial role in the chemical enrichment of the universe, creating heavier elements that would later be used to form planets and future generations of stars. However, the farther we dig into the details of this process, the more uncertainties emerge, and the more we realize how much we don't know. One of the biggest challenges in studying the very first stars is that we have never directly observed one. Their extreme mass and brightness suggest that they would have exploded as supernovae relatively quickly, and any remnants of these stars have long since faded or been obscured by later generations of stars and cosmic dust. As a result, we are left to search for indirect evidence of their existence, such as the chemical signatures they left behind in ancient galaxies. And luckily, the James Webb Space Telescope, with its advanced infrared capabilities, offers the best chance yet of detecting these stars. Telescopes can be time machines. Looking out in space is like looking back in time. It sounds magical, but it's actually very simple. Our universe is bound by the rules of physics, with one of the best-known rules being the speed of light. And when we talk about light, we're actually referring to all the wavelengths across the electromagnetic spectrum, which travel at around a whooping 300,000 kilometers per second. Light travels so fast that in our everyday lives it appears to be instantaneous. Even at these breakneck speeds, it still takes some time to travel anywhere across the cosmos. When you look at the moon, you actually see it as it was 1.3 seconds ago. It's only a tiny peek back in time, but it's still the past. It's the same with sunlight, except the photons, light particles, emitted from the sun's surface travel just over 8 minutes before they finally reach Earth. Our galaxy, the Milky Way, spans 100,000 plus light years, and the beautiful newborn stars seen in James Webb's Carina Nebula image are 7,500 light years away. In other words, this nebula as pictured is from a time roughly 2,000 years earlier than when the first ever writing is thought to have been invented in ancient Mesopotamia. In short, any time we look away from the Earth, we're looking back in time to how things once were. This is a superpower for astronomers because we can use light, as observed throughout time, to try to puzzle together the mystery of our universe. And what makes James Webb spectacular is its great power to see further back in time than any previous instruments. The key to this is related to a phenomenon known as cosmological redshift. As the universe expands, the light from the earliest galaxies becomes redshifted, meaning that it shifts toward longer infrared wavelengths. James Webb's ability to detect this faint ancient light makes it particularly effective at observing galaxies its previous instruments never could. Combine this capability with James Webb's enormous mirror and superb pixel resolution, and you have the most powerful time machine in the known universe. Using James Webb, we will be able to capture the very early universe as it was only 100 million years after the Big Bang, which happened around 13.8 billion years ago. In other words, we will be able to see light from 13.7 billion years ago. So it is understandable that one of the most biggest achievements of James Webb has been its ability to detect and study early galaxies, those that formed within the first few hundred million years after the Big Bang. These ancient galaxies provide vital clues about how the universe evolved in its infancy. Previous telescopes like Hubble could detect some of these galaxies, but the James Webb telescope has gone further, identifying even fainter and more distant objects. In just the first few months of operation, James Webb began delivering breathtaking images and data, revealing galaxies from as early as 300 million years after the Big Bang. These discoveries have shattered previous records for the most distant galaxies ever observed. Some of the galaxies discovered by the telescope are remarkably massive, even though they existed in a time when the universe was still very young. This raises important questions about how such massive galaxies could have formed so quickly after the Big Bang. The unexpected size and brightness of these early galaxies have led astronomers to rethink existing models of galaxy formation. Traditional theories suggest that galaxy formation is a slow process, with galaxies gradually accumulating mass over billions of years. However, Webb's findings hint that galaxies may form much faster than previously thought. These early galaxies could be the precursors to the massive galaxies we see today, or they might represent an entirely different class of galaxies that formed in a more chaotic and rapid process. No matter what the answer is, one thing is for sure: James Webb is rewriting the cosmic book. James Webb's latest surprise may not sound as revolutionary, but it could be the first direct sign of the Tyrannosaurus Rex of stars. The spectrum of one of those distant galaxies shows hints of a huge amount of carbon, much more than could have been formed through familiar stellar processes. The first stars ever to form in the cosmos are thought to have been massive, unfamiliar beasts, and it's believed that Sargon might be a spectral fossil of their bodily remains. But what makes those early stars so exotic? Well, the short answer is that the first generation of stars formed in a more innocent time, before the universe became littered with dust and dirt and adulterated with heavy elements. It was a time when the cosmos was simple and clean, and as a result, star formation was much, much more difficult. In principle, the recipe for a star has a very short ingredient list: hydrogen gas. That's it. The most simplistic description of a star is a giant ball of hydrogen that, via nuclear fusion sustained by the heat and pressure of its own gravity, converts vast amounts of hydrogen into helium, from the lightest element to the next. Stars on the more massive side can also burn other elements in their cores, but they all start the same way. The star is officially born when hydrogen fusion begins in its core, but getting that gas to collect and compress enough to ignite is surprisingly difficult. The problem is, to get enough gas together to ignite and form a star, you have to first, paradoxically, cool it down. The temperature of a gas is really just a measure of how quickly its component particles, atoms or molecules, are moving around. Cold things move slowly, hot things move fast. Imagine you're a sports team coach trying to gather together a group of excited small children into a huddle. As long as they're running around at top speed, they're never going to be able to collect in a group. You need to get them all to slow down first. In star formation, we have a similar problem. Nuclear fusion won't start until you have a lot of gas compressed into very high pressures and temperatures in the core of a dense star. But to get that gas together, first, you need to get it relatively cold. For the stars we see today, this is accomplished mostly with dust. Clouds of gas and dust collect in the denser parts of the galaxy and start gravitating together. As the molecules bounce around and collide, instead of just ricocheting off like billiard balls, some of them can temporarily store that collision energy internally. In some cases, that means the collision causes a molecule to vibrate or flex like a bouncing spring. In others, that might mean an atom or molecule's electrons get excited to higher energy states. Either way, two atoms or molecules can end up going slower than they were before they collided, and they can later release the stored-up energy out into the cosmos as radiation. The end result is that the cloud is just a little bit cooler, and the bouncing gas particles are just a little more chill. That process continues until the gas gets dense enough to form a star. The problem with this story is that the most important molecules for cooling, the ones that can store and re-release energy the best, didn't yet exist when the first stars formed. At that time, the universe was all hydrogen and helium and just a tiny smattering of lithium, all of which formed during the first few minutes of the cosmos. All the heavy elements, carbon and nitrogen and oxygen and the components of that squishy dust can only be formed inside stars or in the supernova explosions at their deaths. So how did the first stars manage to form at all? It is actually possible for gas to cool just with hydrogen, but it's much less efficient and takes a lot longer. Pure hydrogen isn't very good at storing and re-radiating energy. The general expectation among astronomers is that the first stars were much more massive than stars tend to be today, because it takes more gravity to force gas together when it can't cool efficiently. When those massive, pristine stars reached the ends of their lives, they went supernova, exploded in dramatic fashion, and littered their surroundings with heavy elements for the first time. That began the process of filling in the periodic table with heavier elements and made things much easier for subsequent generations of stars, like our Sun. It also allowed for the existence of rocky planets, and, ultimately, us. As James Webb continues to give us glimpses into the most distant galaxies in the cosmos, we're learning more and more about not just physics in unfamiliar environments, but about our own origins in the cosmos. Put simply, we may not yet be seeing the cosmic dinosaurs themselves, but we're picking apart their bones, studying their footprints, and learning more every day about how their deaths made our lives possible. And in addition to early galaxies, James Webb has also made remarkable strides in studying star-forming regions within galaxies. The formation of stars is one of the most fundamental processes in the universe, driving the creation of planets, solar systems, and ultimately, life. However, the details of how stars form, particularly in the early universe, remain poorly understood. The Webb telescope is uniquely suited to studying star-forming regions because of its ability to observe in the infrared. Stars form in dense clouds of gas and dust, which obscure visible light, but allow infrared light to pass through. This means that James Webb can peer inside these clouds, revealing the processes that lead to star formation. One of Webb's early observations included the stunning image of the Carina Nebula, one of the most active star-forming regions in our galaxy. The image, which captured a cosmic cliff of star formation, revealed dozens of newborn stars and dense gas clouds that had never been seen before. The level of detail in these images is unprecedented, allowing astronomers to study the earliest stages of star formation in exquisite detail. By studying these star-forming regions, James Webb is helping scientists understand how stars formed in the early universe. It has already uncovered star-forming regions in distant galaxies, providing a glimpse into the cosmic nurseries that gave birth to the first generations of stars. These observations are crucial for understanding the connection between galaxy formation and star formation, as the two processes are deeply intertwined. But while James Webb solved a lot of puzzles, it also created a few more. Its discoveries have prompted astronomers to rethink the timeline of the early universe. The detection of massive galaxies and active star-forming regions so soon after the Big Bang suggests that the universe may have evolved more quickly than previously thought. This has profound implications for our understanding of cosmic evolution, challenging long-held assumptions about how galaxies and stars form. For example, the traditional view is that galaxy formation began slowly, with small clumps of matter gradually coalescing over time to form larger galaxies. However, Webb's discovery of large, mature galaxies in the early universe suggests that galaxy formation may have been a much more dynamic process, with massive galaxies forming in just a few 100 million years. This raises questions about the role of dark matter and dark energy in galaxy formation, as well as the conditions in the early universe that may have accelerated this process. Additionally, James Webb has shed light on the process of cosmic ionization, a period when the first galaxies and quasars ionized the neutral hydrogen that filled the universe, making it transparent to light. By studying early galaxies, James Webb is helping scientists piece together how and when this reionization occurred. Some of the galaxies observed by the telescope are so distant that they existed during the epoch of ionization, providing a direct window into this transformative period in cosmic history. While these Webb's discoveries is remarkable, they are only the beginning. As the telescope continues its mission, it will undoubtedly reveal even more about the early universe and the processes that shaped the cosmos. The detection of early galaxies and star-forming regions is just one aspect of its vast scientific potential. In the coming years, James Webb will provide new insights into the fundamental processes that drive the growth of galaxies and the formation of stars, planets, and, ultimately, life. One of the most anticipated aspects of James Webb mission is its ability to study exoplanets, planets outside our solar system, in unprecedented detail. Since the discovery of the first exoplanet in 1992, thousands of these distant worlds have been identified, and yet, our understanding of them remains limited. And James Webb's powerful infrared instruments are set to change that, offering astronomers an unparalleled opportunity to study the atmospheres of these planets and assess their potential habitability. By analyzing the light that passes through an exoplanet's atmosphere as it transits its star, the observatory can determine its chemical composition. This process, known as transmission spectroscopy, allows the telescope to detect the presence of gases such as water vapor, carbon dioxide, methane, and oxygen, key markers of potential life. The telescope has already begun studying planets like WASP 96b, where it detected water vapor in the atmosphere, marking a significant milestone in its early missions. As James Webb continues to observe more exoplanets, its data will provide insight into the diversity of planetary atmospheres, ranging from super-Earths and mini-Neptunes to gas giants. For example, one of the most promising targets is Proxima Centauri b, an exoplanet orbiting the nearest star to our solar system. Webb's detailed study of its atmosphere could help answer one of the most tantalizing questions in modern science. Is life possible beyond Earth? Beyond studying exoplanet atmospheres, James Webb will also search for the fundamental building blocks of life, organic molecules such as amino acids and complex carbon-based compounds, in regions where stars and planets are forming. These molecules are thought to be the precursors to life as we know it, and their presence in star-forming regions could provide critical insights into the origins of life in the universe. One key area of investigation for James Webb is the so-called protoplanetary disks, the dense regions of gas and dust surrounding young stars where planets are born. Its infrared instruments are particularly well-suited for studying these disks, as they can penetrate the thick dust that obscures them from view in optical wavelengths. By observing the chemistry of these disks, the powerful telescope will help scientists understand how organic molecules form and evolve in environments that may eventually give rise to habitable planets. Additionally, James Webb will study distant, icy objects in our own solar system, such as comets and Kuiper Belt objects. These bodies are remnants from the early solar system and may contain the same organic compounds that seeded Earth with the ingredients for life. By analyzing the composition of these objects, James Webb will offer new clues about the origin of life on Earth and whether similar processes are occurring elsewhere in the universe. One of the most profound challenges in modern cosmology is understanding the nature of dark matter and dark energy, which together make up approximately 95% of the universe. While these mysterious components of the cosmos are invisible and do not emit light, their presence is inferred through their gravitational effects on galaxies and the large-scale structure of the universe. Despite decades of research, their true nature remains elusive. James Webb has the potential to provide crucial insights into these cosmic enigmas. The telescope's powerful infrared capabilities make it ideally suited to study dark matter's influence on the formation and evolution of galaxies. By observing how light from distant galaxies is bent by massive amounts of dark matter, an effect known as gravitational lensing, James Webb can map the distribution of dark matter with unprecedented precision. This will allow astronomers to better understand how dark matter has shaped the universe from its earliest moments to the present day. In addition to dark matter, James Webb will also study dark energy, the mysterious force driving the accelerated expansion of the universe. By observing distant supernovae and other cosmic markers, the premier observatory will help refine measurements of the universe's expansion rate, shedding light on the nature of dark energy and how it influences the fate of the cosmos. These observations could provide the key to understanding whether the universe will continue to expand forever or eventually collapse in a big crunch. The concept of the Big Crunch is one of the most fascinating and thought-provoking theories about the ultimate fate of the universe. It presents a vision of the cosmos in reverse, where the expansion of the universe slows down and eventually reverses, causing everything to collapse back in on itself. While many current models of the universe favor an endless expansion, the Big Crunch remains a possibility that scientists are still investigating. To better understand the Big Crunch, we first need to grasp how the universe behaves today. According to the Big Bang Theory, the universe began approximately 13.8 billion years ago as a singular point of infinite density and temperature. In an instant, this point exploded, leading to the rapid expansion of space, time, and matter. This event marked the birth of the universe as we know it. Since the Big Bang, the universe has been expanding. Galaxies are moving away from each other, and the space between them continues to grow. This was first observed by the American astronomer Edwin Hubble in the 1920s. He discovered that galaxies farther away from us are receding at faster rates, a phenomenon now known as Hubble's law. This observation provided concrete evidence for the expanding universe, a crucial element in understanding the potential for a future collapse. Gravity plays a critical role in determining the ultimate fate of the universe. While the universe expands, gravity acts as a counterforce, pulling galaxies, stars, and other celestial bodies together. The balance between these two opposing forces, expansion and gravity, will determine whether the universe continues to expand forever or eventually halts and reverses its course. If the density of matter and energy in the universe is high enough, gravity could eventually slow down the expansion. In such a scenario, the universe would reach a point where the expansion stops altogether, and then the gravitational pull would begin to dominate. This would lead to a gradual collapse, with galaxies, stars, and planets hurtling back toward a central point, resulting in what we call the Big Crunch. The Big Crunch is essentially the opposite of the Big Bang. Instead of expanding, the universe would begin to contract. Over billions of years, galaxies would draw closer to one another, and as the universe becomes denser, temperatures would rise dramatically. Stars would collide, black holes would merge, and galaxies would be ripped apart by the overwhelming gravitational forces. As the universe continues to collapse, it would become smaller and hotter, with all matter compressed into an ever-shrinking space. In the final stages of the Big Crunch, the universe would reach a state of extreme density and temperature, similar to the conditions present at the time of the Big Bang. Some theories suggest that this could result in a singularity, a point of infinite density where the laws of physics as we know them break down. That lead the possibility that Big Crunch could create to another Big Bang. This idea is part of a cyclical model of the universe, where the end of one universe leads to the birth of another. In this model, the universe undergoes a series of expansions and contractions, with each Big Crunch giving rise to a new Big Bang. This concept is known as the oscillating universe theory. According to this theory, the universe has no true beginning or end, but exists in an eternal cycle of creation and destruction. While this idea is intriguing, there is little empirical evidence to support it at present, and it remains a topic of ongoing debate among cosmologists. In a dilemma, a piece of good news is the James Webb Space Telescope could provide new data that could help scientists assess its likelihood. By studying dark matter, dark energy, and the universe's expansion rate, James Webb will offer critical insights into the fundamental forces that shape the cosmos. As the telescope continues its mission, it may reveal whether the universe will expand forever or one day collapse in on itself in a dramatic reversal of the Big Bang. In either case, Webb's observations will deepen our understanding of the universe's history, structure, and ultimate destiny, pushing the boundaries of our knowledge about the cosmos and its fate. Whether or not the Big Crunch is in our future, the questions James Webb is exploring will shape our understanding of the universe for generations to come. While much attention has been given to Webb's ability to study exoplanets and dark matter, its core mission, unveiling the mysteries of the early universe, continues to be a major focus. The detection of early galaxies and star-forming regions in the first billion years after the Big Bang has already provided critical insights, but James Webb will go even further, probing the most distant and faintest galaxies to rewrite the history of cosmic evolution. One of the telescope's most striking early findings is the discovery of massive galaxies that formed much earlier than expected. These galaxies, which existed just 300 million years after the Big Bang, challenge existing theories of galaxy formation and suggest that galaxies may have evolved much faster in the early universe than previously thought. This finding raises important questions about the role of dark matter and other forces in shaping the formation of galaxies. By studying these ancient galaxies, James Webb will help astronomers refine models of galaxy formation and star formation. It will also provide new insights into the epoch of ionization, a critical period in the early universe when the first stars and galaxies formed, ionizing the neutral hydrogen that filled the cosmos and making the universe transparent to light. This era marks the transition from the cosmic dark ages to a universe filled with light, and Webb's observations will be crucial for understanding this transformative phase in cosmic history. Although James Webb was not designed to detect gravitational waves, the ripples in space-time caused by massive cosmic events such as the collision of black holes or neutron stars, it plays a complementary role to observatories like LIGO and Virgo. When gravitational waves are detected, James Webb can follow up by observing the electromagnetic radiation associated with the event, such as the light from a neutron star merger. This capability allows the telescope to study the aftermath of these extreme events, providing new insights into the formation of black holes, the production of heavy elements like gold and platinum, and the nature of matter, under extreme conditions. By combining data from both gravitational wave observatories and James Webb, scientists can gain a more complete picture of the universe's most violent and energetic processes. Moreover, supermassive black holes also come into the sights of the James Webb Telescope. Supermassive black holes, millions to billions of times the mass of the Sun, reside at the centers of most galaxies, including our own Milky Way. However, their origins remain a mystery. Fortunately, the ability to peer into the hearts of distant galaxies of James Webb will allow astronomers to study the relationship between supermassive black holes and their host galaxies, shedding light on how these cosmic giants form and evolve over time. One of Webb's early targets is the quasar J0313-1806, a supermassive black hole that existed just 670 million years after the Big Bang. The discovery of such an enormous black hole so early in the universe's history poses a significant challenge to existing theories of black hole formation. By studying this and other early quasars, James Webb will help scientists determine how supermassive black holes grew so quickly in the early universe and what role they played in galaxy formation. As the James Webb continues its mission, it will undoubtedly reveal even more about the cosmos, from the earliest galaxies to the formation of stars, planets, and black holes. The telescope's discoveries are only the beginning, and its data will fuel astronomical research for decades to come. After all, James Webb is not just a telescope, it is a time machine, capable of looking back billions of years to the dawn of the universe. Its observation. The universe has always been a source of endless fascination and mystery.
If you go to the early universe, right after the Big Bang, it was expanding way faster than the speed of light. It's hard to call it a crisis. It is a crisis, but for old-timers, it's really hard. Where we didn't know the age or the size of the universe because they're related.
But now, with its unparalleled ability to peer into the distant cosmos, the James Webb Space Telescope has provided scientists with images and data that have shattered long-held theories in physics, challenging assumptions about the nature of the universe and its origins. These discoveries, in the words of Neil deGrasse Tyson, one of the most recognized and influential astrophysicists of our time, far from being minor revelations, have sent shockwaves through the world of astrophysics and cosmology, pushing the boundaries of what we thought was possible.
The possibility that the Big Bang may be incorrect, and that the universe might be larger and older than we think.
Join us as we dig deep into how the James Webb Space Telescope has fundamentally altered the landscape of modern physics, providing images that many believe have ended some of the most intense debates in the field. To fully understand the magnitude of this discovery, we must first take a quick look at the significance of the James Webb Space Telescope. Often regarded as the successor to the Hubble Space Telescope, James Webb has brought us to the edge of the observable universe. Unlike Hubble, which primarily captured images in the visible and ultraviolet spectrums, Webb was designed to observe the universe in infrared wavelengths. This ability to see in infrared allows the telescope to peer through cosmic dust and observe the most distant galaxies and stars, effectively looking back in time to the early stages of the universe's formation. For years, scientists theorized that the early universe was home to the first galaxies and stars, born a few 100 million years after the Big Bang. But theories are only as good as the evidence that supports them. And James Webb, in the words of Neil deGrasse Tyson, is one of the most powerful tools that would either confirm these long-held beliefs or, as is the case here, shatter them. Neil deGrasse Tyson himself has always maintained a pragmatic view of the cosmos, acknowledging that while much of the universe has been explained, there are still vast mysteries waiting to be uncovered. He often speaks about the scientific method, the importance of changing one's perspective in light of new evidence, and the excitement that comes with the unexpected. With the release of the James Webb Telescope's shattering images, Tyson found himself in the midst of a paradigm shift in astrophysics, one that could rewrite fundamental laws of physics. In various interviews and public appearances, Tyson has expressed his awe at what James Webb has revealed, stating, "The universe never ceases to surprise us. What we thought we knew about the early cosmos has been turned upside down." His excitement is palpable, but behind the enthusiasm lies a profound understanding of the implications of these discoveries. The images that sparked a scientific revolution is unlike anything previously captured by astronomers. At first glance, it is a stunning view of distant galaxies, glowing in various colors, scattered across the cosmos. But upon closer inspection, what truly captured the attention of the scientific community was the discovery of highly developed galaxies that existed much earlier than anyone had previously thought possible. Before James Webb, the prevailing model of cosmology suggested that galaxies took hundreds of millions of years to form after the Big Bang. Stars, gas, and dark matter would coalesce over time to form the first rudimentary galaxies. However, the image captured by James Webb challenges this timeline. The galaxies seen in this image appear to be fully formed, incredibly dense, and rich in complex structures, a level of development that shouldn't have been possible in such a short span of time. According to Tyson, what this means is that our current understanding of galaxy formation is incomplete, possibly even incorrect. These galaxies defy our expectations, suggesting that the processes that created them happened much faster than our models predicted. It's a wake-up call for all of us in the field. Another shocking discovery made by James Webb involves the detection of supermassive black holes in the early universe. These black holes, with masses millions to billions of times that of the Sun, were not expected to exist so soon after the Big Bang. The formation of supermassive black holes is still a mystery to astronomers, but current theories suggest that they form through the gradual accretion of matter over millions or billions of years. However, James Webb has identified several supermassive black holes in galaxies that formed within the first few 100 million years of the universe's existence. This finding has left physicists grappling with a fundamental question: how could such massive objects form so quickly in the early universe? These discoveries are forcing scientists to reconsider their models of black hole formation and growth, and some have suggested that these black holes may have formed through entirely different mechanisms than previously thought. One theory is that these early black holes could have formed directly from the collapse of massive clouds of gas, bypassing the traditional route of star formation. This would represent a major shift in our understanding of how black holes form and grow, challenging the established models that have guided astrophysics for decades. While much of the focus on the Webb telescope has been on its observations of distant galaxies and black holes, the telescope has also provided groundbreaking data on exoplanets, planets orbiting stars outside our solar system. One of the most exciting aspects of James Webb is its ability to analyze the atmospheres of exoplanets in unprecedented detail, potentially revealing the presence of life or conditions suitable for life. The observatory has already made headlines with its detection of complex organic molecules in the atmosphere of an exoplanet located in the habitable zone of its star. These molecules, which include carbon-based compounds, are considered the building blocks of life. While it is too early to say whether life exists on this planet, the presence of these molecules raises intriguing possibilities. Moreover, observations made by James Webb have challenged some of the assumptions about the formation and composition of exoplanets. For example, the telescope has identified several super-Earths and mini-Neptunes with atmospheres that do not match current models of planetary formation. These discoveries have prompted astronomers to rethink their theories about how planets form and evolve, particularly in systems that differ from our own solar system. Elsewhere, James Webb also made a significant impact in the ongoing debate surrounding dark matter, a mysterious substance that makes up roughly 27% of the universe. Dark matter cannot be directly observed, but its presence is inferred through its gravitational effects on visible matter. And Webb's observations have provided new data that has reignited this debate, particularly in relation to the distribution of dark matter in the early universe. Its deep field images have allowed astronomers to map the distribution of matter in some of the earliest galaxies, and the results have been surprising. The distribution of mass in these galaxies does not match the predictions made by current dark matter models. Some scientists believe that this discrepancy could indicate that our understanding of dark matter is incomplete or even flawed. These findings have prompted renewed interest in alternative theories, such as modified Newtonian dynamics, also known as MIND, which suggests that the effects attributed to dark matter could be explained by modifications to the laws of gravity. While the debate over dark matter is far from settled, the data obtained by James Webb has provided physicists with crucial new evidence that could ultimately lead to a resolution of this long-standing mystery. Whether dark matter exists as a distinct form of matter or is the result of new physics remains an open question, but the Webb's findings have undoubtedly pushed the boundaries of what we know. Another foundational theory that James Webb's findings call into question is cosmic inflation. Inflation theory posits that the universe underwent a rapid exponential expansion in the first moments after the Big Bang, smoothing out any irregularities and explaining why the universe appears so homogeneous on large scales. This idea has been a cornerstone of modern cosmology for decades, but Webb's observations are raising doubts. The telescope's ability to look deeper into space, and therefore further back in time, has revealed cosmic structures that are far more complex and diverse than inflationary models would predict. Inflation is supposed to leave behind a universe that is relatively smooth and uniform at large scales, with tiny fluctuations that grow over time to become galaxies and clusters. However, James Webb is showing that structures emerged much faster and more chaotically than inflation allows for, suggesting that something is missing from our understanding of the early universe's expansion. This leads to a profound dilemma. If inflation theory is incomplete or incorrect, it undermines much of what cosmologists thought they knew about the early universe. Some researchers are beginning to explore alternative models of the early universe that don't rely on inflation, though these are still in the early stages of development. In short, the James Webb Space Telescope has already transformed our understanding of the universe in ways that few could have anticipated. Its discoveries have challenged some of the most fundamental theories in physics and cosmology, from the Big Bang model to the nature of dark matter and the formation of galaxies. In many cases, the data obtained by James Webb has forced scientists to reconsider long-held assumptions and develop new models to explain the universe's complexities. However, while James Webb may have ended some debates in physics, it has also opened the door to new ones. The discoveries made by the telescope have raised profound questions about the nature of the universe, questions that will likely keep physicists and astronomers busy for decades to come. As James Webb continues its mission, there is little doubt that it will continue to shatter our expectations and push the boundaries of human knowledge, leading to even more groundbreaking discoveries. Interestingly, while James Webb opens up the far reaches of space down here on Earth, we have another revolutionary tool, the Large Hadron Collider, also known as LHC, at CERN, a powerful particle accelerator that delves into the universe's most fundamental building blocks. One of the LHC's most groundbreaking achievements was the discovery of the Higgs boson in 2012. This particle, often referred to as the God particle, had been theorized since the 1960s by physicist Peter Higgs and others, but it had never been observed experimentally. The Higgs boson is a crucial component of the Standard Model of particle physics, which describes how elementary particles interact with one another. The importance of the Higgs boson lies in its association with the Higgs field, an invisible field that permeates all of space. Particles acquire mass through their interactions with this field, a process that is vital to the structure and stability of the universe. Without the Higgs mechanism, particles would remain massless, preventing the formation of atoms, stars, and galaxies. The discovery of the Higgs boson at the LHC confirmed the existence of the Higgs field, solving one of the biggest mysteries in particle physics and cementing our understanding of why matter has mass. The discovery was a monumental triumph, not only for particle physics, but for science as a whole. It was the final missing piece of the Standard Model, a theory that had withstood decades of experimental scrutiny. The successful detection of the Higgs boson was a validation of countless years of theoretical work and the culmination of a massive collaborative effort between scientists and engineers around the globe. While the discovery of the Higgs boson was a landmark achievement, the LHC's mission did not stop there. One of its primary goals is to probe the limitations of the Standard Model, which, while powerful, is incomplete. The Standard Model does not account for several major phenomena, including gravity, dark matter, and dark energy, which together make up about 95% of the universe. Thus, one of the LHC's key roles has been to search for new physics beyond the Standard Model. Supersymmetry, or SUSY, one such theory, proposes the existence of heavier partner particles for each particle in the Standard Model. SUSY aims to solve several unresolved issues in particle physics, such as the hierarchy problem and the nature of dark matter. Although the LHC has not yet found conclusive evidence for supersymmetric particles, it has placed important constraints on the theory, ruling out a range of possible scenarios. The LHC also probes for clues about extra dimensions, hypothesized in string theory. These extra dimensions, if they exist, could explain the relative weakness of gravity compared to other fundamental forces. Some theories predict that particles called gravitons, which mediate the gravitational force, could leak into these extra dimensions, weakening gravity's apparent strength in our familiar 3D universe. The LHC has yet to detect such particles, but its results continue to inform and refine these speculative models. In other words, the LHC's journey is far from over. As it continues to push the frontiers of energy and precision, the collider may yet reveal new physics that could fundamentally change our view of the cosmos. Regardless, the fact that here in our universe there are some cosmic puzzles that loom very large, casting a grand veil of uncertainty over our attempts to understand all of reality. There's one enormous question of importance on cosmic scales, as well as to those who study nature at an elementary level, that often gets overlooked. Why is our universe and everything in it predominantly composed of normal matter and not of antimatter? We've learned a whole slew of lessons about the universe, what makes it up, what the nature of the various particles and antiparticles are, what rules they obey, etc. And yet we've not once concocted a way to change the net number of baryons, things like protons and neutrons, or leptons, things like electrons, in the universe. But, very clearly, the universe did just this at some point in its distant past. Otherwise, there wouldn't be the planets, stars, galaxies, and more that we observe all throughout the universe. This long-standing mystery has been unsolved for as long as it's been noticed. But the best chance we have to make progress is one that most people wouldn't expect: to build a new, more powerful, more precise particle collider. Here's the science behind this mystery, and why a new collider is our best bet to try to solve it. The puzzle itself is quite simple. Here in our universe, we have the set of fundamental particles whose existence we are certain of, the particles and antiparticles of the Standard Model. They include quarks, which come in the 6 different flavors of up, down, strange, charm, bottom, and top, which have both electric charges and color charges, the antiquarks, which are the antiparticle versions of the quarks, with anti-flavors and anti-colors, as well as opposite electric charges to the quarks. The charged leptons, which are the electron, muon, and tau, with an electric charge but no color charge. The charged antileptons, which are the antiparticle versions of the electron, muon, and tau, with opposite electric charges to the charged leptons. The neutrinos, which come in 3 different species and which have a very tiny but non-zero mass, but that have neither color charge nor electric charge, but always have a left-handed helicity. The antineutrinos, which also have 3 different species, tiny and non-zero masses, and also are colorless and electrically neutral, but always have a right-handed helicity, as well as the bosons of the universe, which include the 8 gluons that mediate the strong force, the photon that mediates the electromagnetic force, the 3 heavy weak bosons, the W and Z, that mediate the weak interactions, as well as the Higgs boson. The quarks and leptons make up all the known normal matter in the universe, while the antiquarks and antileptons have equal and opposite properties and make up antimatter. If you can make 3 quarks bind together, you get a baryon, a composite particle that can be stable, such as a free proton or a neutron inside an atomic nucleus. If you can make 3 antiquarks bind together, you'll get an antibaryon, such as an antiproton. Both of these types of particles, as well as lepton-antilepton pairs, are frequently created in reactions that occur inside particle accelerators and colliders, as well as from natural high-energy processes, such as collisions with cosmic rays. Now, here are 2 facts about the universe that, while both true, are and should be incredibly unsettling for physicists. Fact number 1. Every reaction we've ever created, studied, or measured in particle physics, whether on Earth or in space or anywhere else, has never resulted in a net violation of either baryon number or lepton number. If you create or destroy a baryon or lepton, you also create or destroy an equal amount of antibaryons or antileptons, leaving the total number of net baryons or leptons unchanged. The amount of baryons minus the amount of antibaryons, as well as the amount of leptons minus the amount of antileptons, is always the same, before and after any and all reactions or interactions. Fact number 2. But when we look out at the universe that we have access to, whether we look at what's here on Earth, what exists within our solar system, what exists in interstellar space or in star systems found all throughout the Milky Way, the other galaxies found all throughout the universe, or even galaxy groups, galaxy clusters, or the grand cosmic web, we always find the same thing. All of these structures are made exclusively of matter and not of antimatter. There are no places where matter and antimatter are meeting and annihilating, except as the result of high-energy processes that have produced both matter and antimatter in equal amounts, that shows an interface between a matter-dominated and an antimatter-dominated region of the cosmos. As far as we can tell, all of the universe, everywhere, is populated with roughly the same amounts of normal matter everywhere, with hardly any antimatter to speak of at all. This is one of the greatest open questions in all of physics today, and one of the greatest unsolved physics puzzles about our very existence. But for some reason, and even I myself am not sure what the reason is, this grand existential puzzle has fallen out of favor with the general public. While we still ponder great mysteries like dark matter and dark energy, the extremely puzzling unanswered question of how there came to be so much matter and practically no antimatter in our universe is calling out to us to try to solve it. It's one of the greatest mysteries of all time, and yet, when physicists talk about the great mysteries of the universe, this one often simply gets overlooked. And yet, it turns out the laws of physics aren't completely, perfectly symmetric between matter and antimatter. Sure, this is true for 3 out of the 4 fundamental forces. The gravitational, electromagnetic, and strong nuclear forces don't discriminate. If you have a charged particle moving through an electric field, interacting with a magnetic field, in the vicinity of another charged particle, or even interacting with light, there's no difference between the interactions and effects on matter versus antimatter. If that particle or antiparticle moves through a gravitational field, interacts with a mass, or experiences the passage of a gravitational wave, there's also no difference between matter and antimatter. Although it's far more complicated, the strong nuclear force is no different. Quarks bind together to make baryons exactly the same way that antiquarks bind together to make antibaryons, and quark-antiquark combinations, in the form of mesons, can exist with no trouble at all. But then we come to the weak nuclear interactions and everything looks different. We often say in particle physics that there are 3 symmetries worth considering. There's C-symmetry, or charge conjugation symmetry, which replaces all of the charges, electric, color, and even weak isospin and weak hypercharge, inherent to your system with their opposite charged counterparts, and this is the same, in particle terms, of replacing all of your system's particles with their antiparticle counterpart, and vice versa. There's P-symmetry, or parity symmetry, which replaces all of your particles, or antiparticles with their mirror symmetry counterpart. This is the same as reflecting your system in a mirror and/or replacing notions of front with back, and vice versa, but keeping the other 2 dimensions, up, down, and left-right, the same. And there's T-symmetry, or time reversal symmetry, which replaces a system which runs forward in time with a system that runs backward in time. It's as though you change the direction that time runs, and that reverses your T-symmetry. Now, there's a famous theorem in physics, the CPT theorem, that demands that the combination of these 3 symmetries together, or the equivalent of changing particles for antiparticles, reflecting your system in the mirror and changing the direction that time runs, all at once always leaves you with a system that behaves identically to your original system. And for 3 of the fundamental forces, gravitational, electromagnetic, and strong nuclear forces, the C, P, and T symmetries are all conserved individually as well as together. But for the weak nuclear force, only the combination of C, P, and T all together is preserved. Each of these symmetries, on its own, is violated by the weak interactions. It turns out that the weak interactions violate not just each individual symmetry, C, P, and T, but violate the combination of any 2 symmetries imposed together, CP symmetry, CT symmetry, and PT symmetry. The combination of C and P for the weak interactions is a very close call. Weak interactions that are C-symmetry violating do so at the nearly 100% level. C violation is maximized. Similarly, weak interactions that violate parity or the P-symmetry also do so at nearly the 100% level. P violation is similarly maximized. But when you put these 2 symmetries together and create a circumstance where you've replaced all the particles with antiparticles, and vice versa, and have replaced your original system with the mirror reflection of that system, you find that the amount of C violation and the amount of P violation don't cancel each other out exactly. Instead, there's a tiny amount of CP violation as well, where about 1 in 1,000 particles versus antiparticles reflected in a mirror will behave differently. This is just a 0.1% violation of the CP symmetry, but it turns out to be incredibly important from a cosmic point of view. You see, we might not know exactly how the universe came to possess more matter than antimatter, or why it has the properties that we observe it to have today. But we do know an awful lot about the universe's past, and one of the things we've learned, in general at least, is what is required to create a matter-antimatter asymmetry from a state where none existed previously. It turns out CP violation is one of the key ingredients. That's because there are three conditions that, if you combine them all together, will make baryogenesis, or the creation of a matter-antimatter asymmetry from an initially matter-antimatter symmetric state, not just possible, but inevitable. These conditions were worked out in the late 1960s by Soviet physicists Andrei Sakharov, where the three Sakharov conditions are out-of-equilibrium conditions, such as an expanding and cooling universe that began with a hot Big Bang, the presence of both C-violating and CP-violating interactions, and the admissibility of baryon number-violating interactions. Now, you might look at these three things and have no problem with items number 1 and number 2, as the universe seems to give us both of those in abundance. Not only is the expanding universe an out-of-equilibrium system, but it is perhaps the single most out-of-equilibrium system ever imagined. Things that are permitted and ubiquitous at high energies and early times are highly suppressed and outright forbidden at later times and under lower energy conditions. C violation and CP violation is copious in the weak interactions and can affect a great number of baryons and mesons that contain strange, charm, or bottom quarks and/or antiquarks. It is suspected, but not proven, that this may occur for top-containing or even some down-containing particles or antiparticles as well. However, we've never observed a baryon number-violating interaction. But this isn't impossible. Even within the standard model alone, there's a type of interaction that can do it: the Sphaleron process. Strictly speaking, the standard model doesn't conserve baryon number and lepton number individually, but only the difference between them, the baryon number minus the lepton number. In a practical sense, this can convert 3 baryons into 3 antileptons, 3 antibaryons into 3 leptons, 3 leptons into 3 antibaryons, or 3 antileptons into 3 baryons, and so on. As long as the net number of baryons added, subtracted, and the net number of leptons added, subtracted are equal and come in multiples of 3, this is allowed under the proper conditions within the standard model, either at very high energies or, even though this process would be suppressed at lower energies, through quantum tunneling. That's the first motivation for why we should build a higher energy collider. Although this process is estimated to take place at approximately an energy of around 10 TeV, that's the energy requirement per particle for this interaction to occur. With a combined center of mass energy of 14 TeV for the Large Hadron Collider, this threshold is not achieved, and no Sphaleron processes, and hence no baryon-violating interactions, can occur. With a larger, more powerful collider, for example, a proton-proton collider that can achieve 100 TeV of center of mass energy, this would finally be accessible, and we could see our very first baryon number violating interaction directly. It would be a huge achievement for physics, and for answering a vital existential question, the one about how the very stuff we're made out of, atoms, came to exist over anti-atoms in our universe. Even with this huge carrot dangling in front of us, of creating more baryons than antibaryons, and simultaneously the ability to generate more leptons than antileptons, that's not necessarily the big prize in terms of baryogenesis. It turns out that there's an even deeper motivation for studying this puzzle at a next-generation collider. Sure, seeing baryon number-violating interactions, and lepton number-violating interactions as well, would be revolutionary, and would easily be one of the biggest discoveries in physics of all time. But could the baryon violation generated by sphalerons in the standard model explain the matter-antimatter asymmetry present in the universe today? It could, but only if a certain scenario is true. We've learned that there's an electroweak symmetry associated with the standard model, a symmetry that's restored at high energies and at early times in our universe, but a symmetry that breaks as the universe cools through the electroweak phase transition. If the nature of the transition is first order, which means it gets caught in a false minimum and quantum tunnels into the true minimum, it could indeed explain how our universe got its current matter-antimatter asymmetry. However, if the transition is second order, which is what's predicted by the standard model alone, by the way. This cannot be the full explanation on its own. Some other component or ingredient must be at play. But we already know that the standard model cannot be all there is. Something else must exist to explain dark matter and several other cosmic puzzles that stymie us today. If one of the other things out there has the same quantum numbers as the Higgs, such as a second Higgs doublet, then that can mix with the already discovered Higgs to alter the shape of the phase transition. Even if that second doublet is at much higher energies, even if it's out of reach of the LHC or even a proposed future collider, the effects it has on the electroweak phase transition can still render it strongly first order, as opposed to the second order transition predicted by the standard model alone. If we want to know whether baryon number-violating interactions exist, as predicted by the standard model, a next-generation particle collider is an essential tool. If we want to probe the nature of the electroweak phase transition and find out whether it's first order or second order, a next-generation particle collider is the tool we need for that job. And if we want to determine whether the matter-antimatter asymmetry that exists within our universe was created during the electroweak phase transition long ago in our cosmic past, a next-generation particle collider is arguably the only tool that can reveal the answer to that question. It's the one cosmic secret that absolutely demands that we build a next-generation collider if we hope to find the answer. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. The rocky cores with liquid water oceans. If future observations confirm the presence of water oceans beneath the atmospheres of mini-Neptunes, these planets could represent a new type of potentially habitable world, one vastly different from Earth but still capable of supporting life. The search for exoplanets often focuses on finding planets within the habitable zone of their parent stars, the region where conditions are just right for liquid water to exist on a planet's surface. One of the most exciting recent discoveries in this regard is Proxima Centauri b, the closest exoplanet to Earth, located just 4.2 light-years away. Discovered in 2016, Proxima Centauri b orbits its star within the habitable zone, and recent studies suggest that it could have a rocky surface with liquid water. Although Proxima Centauri is a red dwarf star and its planet is exposed to intense stellar flares, making habitability a challenge, its proximity makes it a prime target for future observations and potentially even exploration missions. Another exciting discovery is the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a red dwarf star located about 39 light-years from Earth. 3 of these planets lie within the habitable zone, where conditions could allow for the presence of liquid water. The TRAPPIST-1 system has captivated astronomers since its discovery in 2017 because all 7 planets are roughly the size of Earth and could have atmospheres suitable for life. The James Webb Space Telescope is expected to conduct detailed studies of the TRAPPIST-1 planets, providing insights into their atmospheric compositions and potentially identifying biosignatures. Another intriguing category of exoplanets that has emerged from recent discoveries is ultra-short period planets, or planets that orbit their stars in just a matter of hours or days. One example is NGTS-10b, a Jupiter-sized gas giant that orbits its star in just 18 hours. Located about 1,000 light-years from Earth, NGTS-10b's close orbit causes its atmosphere to be extremely hot, with surface temperatures reaching thousands of degrees Fahrenheit. While such planets are unlikely to host life, they provide valuable insights into the extreme conditions that can exist on exoplanets and help refine models of planetary formation and evolution. Another ultra-short period planet of interest is TOI 849b, a naked planet core, discovered by TESS in 2020. TOI 849b orbits its star in less than a day, and is believed to be the exposed core of a gas giant, stripped of its atmosphere by intense stellar radiation. This discovery offers a unique opportunity to study the interior structure of a planet, as TOI 849b provides a rare glimpse into the composition of a planet's core. Understanding the makeup of this planet could help scientists learn more about the processes that shape the formation of gas giants and their eventual evolution. While many exoplanet discoveries have been made within a few hundred light-years of Earth, recent advancements in telescope technology have allowed astronomers to detect planets orbiting stars much farther away. One such discovery is OGL 2016 BLG 1195LB, a planet located more than 13,000 light-years away. This planet was discovered using a technique called gravitational microlensing, which relies on the gravitational field of a distant star to magnify the light from a background star, revealing the presence of an orbiting planet. OGL 2016 BLG 1195LB is similar in size to Earth and orbits a star in the outer regions of the Milky Way, providing valuable data about the distribution of planets across the galaxy. Another distant discovery is Kepler 1649c, a rocky exoplanet located about 300 light-years away that orbits its star within the habitable zone. Kepler 1649c is similar in size to Earth and receives about 75% of the sunlight that Earth does from the Sun, making it one of the most Earth-like planets discovered to date. Although its distant location makes it difficult to study in detail, Kepler 1649c remains a prime candidate for future research, as its Earth-like characteristics make it a potential target in the search for extraterrestrial life. Fascinatingly, the launch of the James Webb Space Telescope in December 2021 marked a new era in exoplanet research. One of the most groundbreaking contributions of James Webb to exoplanet research is its ability to analyze the atmospheres of these distant worlds. By observing transiting exoplanets, those that pass in front of their host stars from our viewpoint, James Webb can measure the light that filters through an exoplanet's atmosphere. This technique, known as transmission spectroscopy, allows scientists to determine the chemical composition of the atmosphere, identify potential biosignatures, and assess habitability. For example, James Webb's early observations included the atmosphere of WASP-39b, a gas giant located about 700 light-years away. The telescope detected water vapor in the atmosphere, confirming the presence of this essential molecule for life. This discovery not only demonstrated James Webb's capabilities, but also set a precedent for future studies aimed at characterizing the atmospheres of other exoplanets. By identifying other molecules such as carbon dioxide, sodium, and possibly even methane, James Webb is providing crucial insights into the conditions present on these distant worlds. Additionally, Webb's sensitivity and advanced spectroscopy techniques allow it to search for potential biosignatures in exoplanet atmospheres. Scientists are particularly interested in detecting molecules such as oxygen, ozone, methane, and carbon dioxide, which can suggest the presence of life. One exciting aspect of Webb's mission is its ability to simultaneously detect multiple biosignatures. For instance, a simultaneous detection of both methane and oxygen in an exoplanet's atmosphere could indicate the presence of biological activity, as these gases tend to react chemically and are often replenished by living organisms. This dual approach to biosignature detection represents a significant advancement in the search for extraterrestrial life. Moreover, Webb's capabilities extend to rocky, Earth-like exoplanets, particularly those located in the habitable zones of their host stars, the regions where conditions might support liquid water. The telescope's sensitivity and advanced imaging techniques allow it to search for potentially habitable exoplanets with greater precision. One of the most anticipated targets for James Webb is the TRAPPIST-1 system, which contains several Earth-sized planets orbiting a cool dwarf star. By studying the atmospheres of these planets, scientists hope to gather insights into their potential for supporting life. The ability to analyze the atmospheres of these worlds opens the door to assessing their habitability and searching for signs of life, marking a significant leap forward in our quest to find another Earth-like planet. Additionally, the Webb telescope is expected to focus on other intriguing targets, such as Proxima Centauri b, the closest known exoplanet to Earth, and LHS 1140b, a super-Earth located approximately 40 light-years away. These observations could provide critical data on the conditions present on these planets and their potential for habitability. In short, with its advanced capabilities, James Webb is poised to significantly expand our current catalog of exoplanets. Its sensitivity and range will enable astronomers to discover more exoplanets, including those that are smaller and more Earth-like than previously detectable. This will contribute to a more comprehensive understanding of how planetary systems form and evolve, potentially offering insights into the origins of our own solar system. Moreover, observations made by James Webb will complement and enhance data collected by other missions, such as TESS. As TESS continues to discover new exoplanets, James Webb will provide the means to analyze their atmospheres and characteristics, creating a more holistic view of exoplanet science. Put exoplanets aside, there is a new, remarkable observatory made by the aging Hubble telescope. At the center of almost every large galaxy in the universe sits a supermassive black hole, and any surrounding clouds of gas, dust, or even stars that wander too close are consumed as they cross over the event horizons of these cosmic monsters. When supermassive black holes gorge on large volumes of energy and matter in this way, they become capable of creating massive jets of plasma that are shot out through space at close to the speed of light. For instance, one such galaxy, Messier 87, which is roughly 54 million light-years from Earth, is home to a 6.5 billion solar mass supermassive black hole, which produces 3,000 light-year-long jets of plasma. And new research, based on observations made by the Hubble Space Telescope, has found that double-star systems sitting close to these jets are living pretty risky lives. Stars can often find themselves gravitationally bound to one another, forming double-star systems. And sometimes an aging, swelled-up normal star can find itself with a white dwarf companion, the dead embers of a once active star. In such scenarios, the enlarged star can shed its materials, mainly hydrogen, which are gravitationally drawn to the dense white dwarf. However, as hydrogen accumulates on the surface of the white dwarf, the star can reach a critical tipping point. After that point, the process spurs an explosion. You can think of it like a hydrogen bomb. Such explosions are called nova, and they are relatively common throughout the universe. In fact, one is expected to happen quite soon, with a star called T Coronae Borealis. And, in a rare turn of events, scientists think that explosion will be bright enough to make a new star show up in our night sky. Intriguingly, astronomers found that nova eruptions are almost twice as likely to occur in double-star systems located in the vicinity of Messier 87's supermassive black hole plasma jets. Initially, astronomers thought something about the jets might be enhancing the fueling process and therefore the rate of explosions, or even birthing new double-star systems in its vicinity. But Alec Lessing, an astronomer from Stanford University and lead author of the paper reporting on these findings, isn't quite convinced. According to Lessing, "We don't know what's going on, but it's just a very exciting finding. This means there's something missing from our understanding of how black hole jets interact with their surroundings." Not long after Hubble was launched in 1990, astronomers pointed the telescope towards the center of Messier 87, where the galaxy's supermassive black hole dwells. At the time, they observed strange blue transient events near the black hole, but the narrow field of Hubble's camera at the time meant the scientists couldn't compare how often these events were occurring in that location when compared to the rest of the galaxy. In the words of said co-author Michael Shara from the American Museum of Natural History in a press release, "We're not the first people who've said that it looks like there's more activity going on around the M87 jet. But Hubble has shown this enhanced activity with far more examples and statistical significance than we ever had before." The evidence for the jet's influence on the surrounding stars was collected over a 9-month period, with Hubble observing with its newer, wider-view camera every 5 days. Despite nova eruptions being common events in galaxies as a whole, the new research further illustrates the influence that supermassive black holes can have on activity and evolution of galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.